Okay. All right, can everybody hear me, even those on Zoom? Thank you. I'm asking about those who are on Zoom. Can you hear me?
Yes, we can hear you. We can hear you.
Okay, perfect. Thank you. So what I need to do is to start class. All right, I think we are ready. Just as a short introduction to what we covered last time, and so you stay connected with that, is that as we are going through magnetostatics, I would like you to remember the duality that we have seen between electrostatics and magnetostatics. And also you will see what I will do as we go through that. I will speak more about the physics involved rather than the equations that describe the physics, all right? Because I would like you, while you remember the equations, I would like you, when you see an equation, to think physics. And I don't know exactly what's the best way to think of physics with me is that I visualize it somehow, all right? I try to visualize the physics behind it. And I will try to tell you how I'm thinking about it. So for the following reason, I think if you understand the physics of any problem, all right, if you are comfortable with that, you may not necessarily present the most accurate solution, but your solution is going to be accurate within an engineering error. If you work only with equations and you don't understand the physics, your answers can be way out there. And not only that, but if you give those answers to somebody else in your professional environment, they're going to think that you have no clue of what is going on. And there is nothing worse, all right, in terms of reputation damage as an engineer, but others to think that you have no clue. It's better for you to have a clue and you give an answer which is not exactly perfect, as opposed to the other way around, okay? So that's what I'm trying to help you with here. And I know it takes time. So let's start with this, electrostatics. What we've seen in electrostatics, what source generates an electrostatic field? Who is gonna help? Somebody is gonna say something? A charge, but what charge? Yes, static charge, stationary. All right. And when you have a charge sitting somewhere, it creates an electric field, E. And from the electric field, the right word is electric field intensity, all right, is a vector. We define electric flux density, D. And D is a function of E, is a scalar multiplied with the electric field. And why is this a scalar? Because all of the materials, of course, including vacuum, but all of the materials that we're going to use in this class are going to be linear, means the material, the properties do not change with time. Uniform, homogeneous, rather, as we call it, which means that wherever you go, the epsilon constant is going to be the same. And isotropic, what does that mean? Whatever direction you look at, if you are sitting in one place, whatever direction you look at, the epsilon is going to be the same. all right? So if you satisfy all of these conditions, your epsilon is a scalar, and for materials in general, it's going to be epsilon equals epsilon sub r times epsilon naught, where epsilon naught is the dielectric constant for free space, and we know it. Epsilon naught for all of the dielectrics that we know, and here we don't have any losses or anything in the dielectric, are perfect dielectrics, all right? Epsilon r is a real number. For all of the dielectrics that we know, the most useful ones that we are working with, epsilon sub r varies from above 1 to like about 15. So for example, for duroid is about 2.7, 2.4 to 2.7. For quartz is about, glass rather, it's about 4. For silicon is about 11.7. For gallium arsenide is 12.4. And then maybe there is something else, graphene, like whatever. If you go to this kind of dense materials, you have different characteristics, but the ones, for example, that we know that they have epsilon sub r that varies between, say, 1 and somewhere in the teens. If we look now at magnetostatics up to here, so a magnetostatic field, H, is created by a charge that moves with a constant velocity. Always charges create fields, but this one charge moves with a constant velocity and therefore creates a current. And currents do not, they are not finite. I mean, from minus infinity to plus infinity. Currents come and close in loops. Why is that? Because if you have a charge then in a system that is moving, somehow the system has to stay in equilibrium in terms of the total charges. They have to cancel out. And therefore, you cannot just keep losing charges, all right? If you are in a system and then you have a charges that are moving, you cannot just keep losing them. You have to supply them. So either you're going to have a source or the current is going to move around, all right? So usually currents are closed. They run on closed paths. And somewhere on this path, you will have a source, okay, obviously. Okay, so we have, in case of that, of a steady current, like a charge with constant velocity in magnitude, then we create a magnetostatic field. And then we have a magnetic flux, which is also the scalar mu times the magnetic field. And if the material is, as we said, linear, homogeneous, and isotropic, then mu is a scalar. And mu is going to be mu sub r times mu sub naught, where mu sub naught is for free space. But mu sub r, which is for good magnetic materials, is a very, very, very large number. So 10 to the 5th, 10 to the 6th, all right? It's not like from 1 to 15. It's a very 1,000 and above for any decent magnetic material. Okay, so that is one thing to keep in mind. Another thing before we move, in fact, as we move here, what does this one say? Gauss's law. When you look at these, what comes in mind? What do you visualize when you see that the divergence of G equals the charge? You know what I visualize? I visualize a charge and all of the field lines coming out of the charge, positive charge. That's what I visualize. And why is that? Because this is a flux. When we say flux density, what do you think? I think it's like the flow of energy out of a charge. This is how I connect, all right, flux. It's an electric field intensity, obviously. The units are appropriately, all right, developed. But the way I think about it is like how much really energy leaves a charge. And usually, of course, whenever you have an electric field, you have electric energy, of course. But the flux shows, as the word says, if it goes, how this goes out, all right? And what that tells us, Gauss's law tells us that when you have a charge and a positive charge, then this flow of electric field or electric energy is going to come out of the charge. And those lines that show the direction this flow has, they will terminate on another charge. Or they will keep going to infinity if there is no other charge. But if there is another charge which is negative, if your original is positive, will terminate there. And if you have another charge which is positive, your lines from your positive charge will not terminate in the other positive charge. They will go around and terminate somewhere in another negative charge they find. All right? That's the kind of visual you need to have and the understanding of what that means. What is the other property underneath it mean? That the curl of E is 0. It means, go ahead.
It flows in a straight line.
Yes, you don't have loops. Your electric fields do not have loops. All right, don't. So they go straight lines until they meet an appropriate charge. Okay, so that's what it says. And what is the last one? What does the last one say? Which we found it, of course, this is divergence theorem used on Gauss's law, right? Practically, but what does it say really? It says that if we have a field, an electric field here, somewhere has a source, right? But we see, let's assume that we could see, I mean, I was thinking, what if we could only see electric fields like green lines, and we see magnetic fields like, or electric fields like red lines and magnetic fields like green lines. Let's assume that we have sensors, doing electromagnetic sensors instead of eyes. Or if we had another, like some sensors up here, and we could see electromagnetic field, that would have been an interesting evolution. Didn't happen. But in any case, then I could see all of the electric field lines that go here. All right, and then I go and I define a volume, and then I integrate on this volume the flow, this divergence that shows the flow, all right, of my field lines. What am I going to find? If there is no charge inside this volume, then the lines will come from one side and they will exit on the other side, all right? If there is a charge in this volume, positive or negative, what is going to happen? My lines, if I come from a positive charge and then the positive charge is in the other room, but and so the electromagnetic field is here, but then there is a negative charge inside my volume. What I will find out is that the electric field lines from this other positive charge, they terminate on the negative charge. So they never go out of the volume. They come in, but they don't go out. So that means that when I try to integrate all of this flow, I'm going to find something which is different than 0. And obviously, it's going to be a measure of the charge within the volume. However, if all of my charges are far away, and I see the electric field, and I integrate all of these flux lines in a volume which does not have a charge, whatever flux lines come in, whatever energy goes through the volume goes out. All right? Whatever comes in goes out. And therefore, that's going to be 0. That's what it says. So a lot of times, if I know the electric field, if I could see the electric field, but I could not see the charges, then I would integrate in the volume of interest, and then whenever I would find non-zero, then I know that I have a charge in there. So that is what that property tells me. Now let's go to magnetostatics. What does this tell me? That the divergence of B is 0, it tells me what? It tells me that the magnetic field lines do not start anywhere and do not terminate anywhere, which means they will close. They're closed lines, right? Or in other words, there are no magnetic charges where the lines start and terminate. I told you last time, I don't know whether it was this section or the other one, that a lot of times we get confused because we look at some magnets and then you see magnetic lines starting at one pole and terminating on the other pole. And you say, well, what does that mean that I have? No, they don't terminate, they go through the material. All right, they go through the material. They don't terminate. We think that they terminate, but in reality, they go through. Okay, so that's what the first one says. What does the second one say? The second one says, first of all, since the curl of the H field is not zero, it says that they rotate. They go along rotational patterns. What is the other thing that they say? That they will go, that if I have a source, a current as a source, then all of these rotational patterns will just circulate the source. All right, that's what the second one says. And the last one, which is Stokes' theorem, and comes out of Ampere's law, what does it say? That if, therefore, I have a magnetic field that circulates a source, and let's assume my source is like this current, and then I have a magnetic impedance, and I have a magnetic field that circulates it, never crosses it, never never touches it, circulates. Even if it's a finite current like this, it will circulate around it. Then that tells me the Stokes theorem that applies to Ampere's law to give me that. It says that if I integrate the magnetic field line around my source, then it's going to be equal to the current that has created it. Okay. And then the last thing that I would like to say is the following. Every problem in real life we have that involves electronics, and also whether there are circuits, antennas, and the whole thing, they are all three-dimensional structures. Even when you have a CMOS, which is about, what, 22 nanometer gates, and then you go, and then you look at this from close enough, then you will see that is a 3D structure. Now, we could not have electronics like my cell phone or your cell phone that has billions of transistors in there. If we had to go and look at a billion 3D structures, there's no computer that it would be even today. There would not be, we would not have a computer to be able to do this, which implies that for us to be able to solve complex problems, that we have to go from three-dimensional objects that are electrically important to what we call the symbolic representation. What is a symbolic representation? Symbolic representations are like the capacitors, the inductors, or the resistors. So to show you here, symbolic representations is, one is this resistor, the other is this capacitor, and we've seen 3D capacitors, and the other is this inductor. All right, so practically, and when you go to actives, you have similar symbolic representations. So practically, you take a very complex structure, and then you identify one symbol to represent it. These are two-port structures. If you have three-port, you may see something like this. Okay, that's a transistor. So by doing this, we can leave this extremely dense complexity and go to something simpler, and that's how we solve problems. All right, so the whole idea here in this class is not to get ourselves lost in 3D, but to be able to translate 3D and fields that are what really happen in reality into symbols then we can use which retain the way we define them, they retain the fundamental properties, all right? So a resistor means that as the current goes through, you lose energy. All right, and then by defining the resistor correctly, then you define the energy you lose correctly, the power you lose. By a capacitor, this little thing that shows a capacitor, if you define the capacitance, it tells you how much charge it stores in the capacitor when you operate it. And then usually the capacitor will charge and then discharge, and then charge, you know that, how much, and takes some time to do that. And then inductance, the same thing. How much L tells you how much magnetic field is stored in your 3D structure, but you show it with this little coil. And then you have L to work to, and then we have circuit laws, which are convenient, and then we can solve huge structures. Now, how do you go from an RLC plus a transistor to like billions of transistors? Then we are smart to do the following. Don't think that I'm going to go in a computer and put all of these billion transistors and then trillion resistors and another trillion capacitors and another trillion inductors. That's not happening, not going to work. So what do? We work small pieces like building blocks. So an RLC circuit is one building block. A CMOS with some circuits around, like it can be you can create TIAs from them, all right? So you take small building blocks and then you use them to create intermediate building blocks. And then you use the intermediate to create bigger building blocks. But all of the building blocks, like a brick, they're all identical. So then it's easy to use them. Otherwise, there was no way that we could have done something more complex than an RLC circuit in the lab practically. All right, so all of this discussion, because I want you to think it that way, all right, to see the equations, but ask yourself what is the physics. And now we are gonna go, and I think we've done that last time. We are gonna go and think of very specific sources that create magnetic fields. So one is what we call a filament of current. So it's a current that flows, it's of course ideal. It flows on a very long line. It does not start and stop, it closes somewhere far away from us. We don't see that. So when we observe the line, it looks like a straight line. And with that in mind, we found last time that the magnetic field, which is created from this line, here, if D is the distance, you see, I find myself, I go to a point in space here, there. Let's assume that that's where I am as an observer. So my distance from the current is D. And I measure the magnetic field. What I find is that the magnetic field changes as 1/D from an infinite long current. What does this remind me? Here is how to do an example. And I want you to look at the examples, all right? Because I did this example so you can see and remember that you always have to put units next to whatever values you calculate. Okay, what does this remind me? Now, duality, you remember I said electrostatics and magnetostatics have a lot of duality in them. So if I have a charge Q here, all right, and assume it's positive charge, and we have seen that problem, it goes on an infinite long line, charge forever. Then we found that in this problem has cylindrical symmetry, which means no matter how I move around it, I see the same field if I am at the same distance. And no matter how far up in terms of Z or down I go, I see still the same thing. So what happens with this, if I go to a point here, then the electric field lines leave along the radial direction, and they vary as 1/D. if I go to the magnetic field case, so instead of a charge, an infinite line charge, I will have a current filament. When I say that, it means current that's very thin, and then it looks straight to us, goes very far away. Then this current, which is a steady current, creates a magnetic field. The magnetic field here, as we said, does not touch the current. It circulates around it. Circulates all this around all of these paths. And it has not the R component, but it has the phi component. Remember, the phi component goes exactly as you see here, like this. That's a phi component in the cylindrical coordinate system. You remember that? And this phi component of the current is given by I, which is the current, divided by 2 pi d. So it also changes as 1 over d. So infinite long charge and infinite long current, the fields they create have different directions in their components. However, they vary as 1 over the distance. Important. All right, now let's go qualitatively at this moment, without even having solved this problem, to find out how would based on what we know, how would a magnetic field behave that is generated by a circular current. So we call it a current loop. So let's assume that this current goes around a circular path. Okay, from what we know, first of all, the magnetic field lines are not going to touch the current. And that means that they are going to go around the current. And the closer you go, like if I were to show all of the lines, and if I go here, it will look like this. All right, but as I go further away, it goes and looks like that. And the same thing here, it will look like this. But as I go further away, it looks like this. And what pushes this current, instead of being symmetric like it is on an infinite long current, this one loses its symmetry. And why is that? Because of the contributions of all of the current segments that are around this circle. All right. Now, we can solve this problem. And how I would solve the problem? In this particular case, I cannot use, obviously, like we did with charges, all right? If you have a charge that is like a circular charge, you cannot use, you don't have a particular symmetry, so you cannot use, in that case, Gauss's law. And for the same reason here, since our current flows on a loop, we're not going to be able to use Ampere's law. So we have to go to the original laws. For statics, for electrostatics, is Coulomb's. And for magnetostatics, how do we call this law? Which is here in equation 1. What is the name? Biot-Savart. All right. It's more complex, obviously, because it shows us exactly what happens if we take a very small section of this current, which we call DI, and it's here. If we take this little green part of the current, and of course, it's going to have a direction, and the direction will be the phi direction because it goes on a circular path, all right? Then, Biot-Savart, it tells us, this law tells us that this infinitesimally small current source is going to create an infinitesimally small field, magnetic. And then it shows the magnetic field in terms of the magnetic flux density, B. All right. So the infinitesimally small field is given by this expression. And now what we will have to do is to integrate along the circle, which in fact is going to be easy to do. You just have to identify a place where you want to observe your field. And then what we did in this particular case, we are identifying a point on axis that goes through the center of the circle. And why did I do that? Because it's simpler. If I don't do it like that, then it's going to be very messy mathematically. You can do it if you write a program though, okay? But I'm going along the axis, and you will see that that is going to be very useful to go along the axis eventually, as we will try to calculate the inductance from a loop like this. So you split AB, which is the distance anymore, all right? So you go on point B, which is here. Then your distance from your source is going to be AB. AB is here. Then I have a triangle here, which is like a orthogonal triangle. You write these expressions. You plug in, you will see are very simple expressions, and then you come up with two. Each segment of current creates a magnetic field that has two components. One component is along the z direction, and the other component is along the rod direction. All right, that's what you find. And if I wanted to find the whole field, I have to make the following observation here. So instead of trying to use both components and then try to integrate for both components, I observe that my radial component is practically going to be canceled out. Why is that? Why are you guys smiling all the time? You make me wonder. Be focused. I know it's Friday. Everybody wants to go home, myself included. All right. We are all tired, but could you just hold it a little bit? Because then I would need to know why you're laughing so I can laugh myself with you. Because we all need some kind of, I understand. It's kind of the end of the week. Plus it's cold outside. All right. So what we need to realize on this picture, and I will go here, is that this B, all right, B, which is excited from the infinitesimally small current, is perpendicular to the line that connects A to B and can be split in two components, one which is the radial component and is parallel to the circle, and the other which is the Z component. All of these segments of current along the circle will contribute to the same Z component. So we know that all of those will create a Z component. But all of the radial components, see, if this one creates a radial component like that, the opposite, diametrically opposite, is going to create a radial component which is in the opposite direction. So all of the radial components will cancel out. So the only thing that remains on this axis is the Z component. All right. And if I integrate around, that gives me this expression. What is the interesting thing about this expression? If D, let me see what I have selected as D. D is Z, is the Z coordinate. Let's look at when the Z coordinate is 0, which means if my D is 0, all right, here, that means that I am on the surface of the loop, but at the center. So I'm right at O. When D is 0, the observation point B goes down here and finds itself at the center of the circle. And when that happens, at the center of the circle, I can simplify things. And what I find from here, when D is 0, then I have that B is still along the Z direction always. It's going to be mu I, and then I will have A squared over 2A cubed. All right, and then this and that will cancel, and it's gonna give me AZ nu over 2A I. So it's an inverse of the radius. Why is this important? Okay, now let's see. What is going to happen if I try to find from this loop, which I will show it here. Okay, that's not exactly correct. All right, this is the current. Now, let's assume that I want to, now that I know that I have these magnetic fields that go like here. All right, you remember how they look? They look like this. And this. And then here like this. Okay, if I were to go on the surface of this disk, all right, I don't go that far up, but I just go down to the surface. What am I gonna see? That on the surface of the disk, the only components that I have right on the surface will be perpendicular, all right? Because here that continues like that. So that tells you that as they go through the surface, they are all perpendicular. So for example, you're gonna have here one, here another one, here. But they are all perpendicular. There are no horizontal components of the magnetic field on the surface. All right, because if they were, what will happen? They will have to cross the current, which they cannot touch it. So they go all like that. Okay. Let's see what happens outside. All right, so I will take, in fact, only one line here, because I cannot do it. It's going to be a little complicated if I do it for the whole. I'll take this line, and then I will look at the current here and the current there. And then I will try for these two segments of the current to plot the fields, all right? So one current goes like this here. The other current goes like this there. All right. So if I were to plot only the B field on the red line, this one, and I call it X, what I will find is the following. Let me do it here. And then let's assume that this one field is here, and the other is there, current. One current goes in like this, and the other current comes out like this. All right. Now I'm plotting the magnetic fields. Will be strong here because they both add. Then let's look at this side. It's gonna be probably something like, there's gonna be, they will go down, but not very fast. And then when you come here, go like this. And then what happens? When you go out, the direction of the field is gonna be like this. Let me see. No, red. Gonna look like this. Right, and the same thing is gonna happen from the other side, and then they will grow. And the same thing is gonna happen from the other side. Okay, so now you can say, why do you think that's important? Well, and in fact, to be also accurate, because this is kind of confused, I have not been very truthful to what I said. They will go like this, but they will remain small. And then they will go down because you go far away from your sources, all right? All right, so they will remain small and they will go like this. And then eventually they will go down to 0. So you have that. That's how it's going to be. And I will give you a problem where I will ask you to plot it so you get a sense, because this loop is a very important one for inductances. Now, why is this important? And why do I not look at all of the other places, but I look at the center? Because of the following. The change of the magnetic field in the center of the loop, around the center, is kind of flat. All right, it's flat. It starts moving out here faster, all right? But it's more or less, it goes on a very smooth slope like that. When I find an inductance, how do I define the inductance? I define it as the total magnetic flux divided by the current. Now let's think for a second how we define capacitance. How did we define capacitance? Q over V, you remember? However, do you remember what was Q? Let me show you here. We started with the initial equations. What was Q? Q was the total charge that comes from what? From integrating the electric flux density. So practically Q is an integral of the flux density around the volume, all right? It incorporates that Q. So you could say that the capacitance also is an electric flux, the total electric flux density through the volume. So if this is magnetic flux, then I will say this is really that, even if you don't see it very often like this, you see Q over V. But in reality, they're both about a flux density. It's how much energy, gets out of a particular volume, and that divided by the voltage that applies between whatever charges you have that have created that field. In the case of electrostatics, gives you capacitance. In the case of the magnetostatics, you look at the flux, magnetic flux, like the magnetic energy that really is created because of the current. You integrate that of whatever surface you have, all right, which is like the surface that will cover the area of the circular loop plus more around it. And then you divide it by the current. And that's an inductance. So practically in this one, why is this practical? Because in reality, I can go here and create this current by coming here with a wire that goes like that. Then I go here and I can have another wire. So the current can go like this, sorry. The current can go like this and then come out on the other side like this. That's a very practical loop. It's one inductor, one loop inductor, all right? So you have the input current coming and leaving and probably connected to whatever, a battery or something that generates it. So if I want to find the inductance, because we said we want to replace it, we want to find something to show it symbolically. In a circuit environment, we symbolize that with an inductance. We show it like that. How would I find the inductance? I would have to integrate, take a whole surface that has the conductor, that covers all of this conductor, take the surface of the current, take the surface and all around it, integrate it and then divide this by the current. But see what happens here. You see what happens here? If I integrate the flux, most of the flux goes up here, and at this point reverses and goes down. So what is going to happen? When I sum up those fields here towards the contribution of flux from the areas around the wire are zero practically, because they cancel out. This contribution here is going to cancel out from these contributions there. All right? And then those become very small. So when I start looking at the flux, and if I want to see how the flux is going to look like, I go back to this one. Okay, and then I put here the two wires that come in and out. If I plot the flux, and if I use, say, or green, dark green, where the flux is very strong, then you're going to see that the flux is going to be here, strong. Let me see, I'll do that first. So practically, it's going to be all here, but most of the contributions, because the other outside will cancel out from the contributions near the wire, all of the contributions will come from here. All right. All of the contributions will come from there. And the best approximation is to assume that the field that gave you this flux is constant and equal to the one at the center. So we calculate with this kind of engineering approximation, we calculate. So the flux, if I were to look at the total flux, is going to practically come out of this part of the circuit, all right, where I have the dense color, which means I can ignore all of the outside, and I can ignore what happens very close to the wire. And therefore, I can find the value of the magnetic field at the center of the loop, and then integrate that constant on the surface of the loop, which practically what is going to give me, and then you can find a very simple formula. So it's going to give me, if this is at the center of the loop, is mu I over 2a. Oops. I go here and I say, now my flux is going to be pi I, did we say 2a? And then it's going to be, does it have a pi? Let me think. Mu I, not pi I. Mu I over a. And then the area of the loop, pi a squared. So the flux is going to be mu I pi divided by 2. And how much is going to be the inductance of this loop? Mu pi over 2, because it's phi sub m divided by I. Now you found an inductance. Yes.
What about the other?
What other?
The other A.
Yeah, you have pi squared divided by 3.
Ah, yes. Thank you. I forgot that. Okay. So now we found something very useful using a few steps